Hello everyone, I'm Diego Ochoa from Power SmartCtrl, and today I'm going to show you how to design let's share the screen. Okay. And today I'm going to show you how to design the output voltage loop in order to control the series resonant converter. So let's start. This is a brief description about what is smart control. So smart control is a tool that allows to design in an intuitive and simple way the control loops for the power electronic converters. This tool is very useful in sectors such as education and industry, for example. Smart control also adapts to different levels of knowledge, as there are three different ways to define the converter plan. Once the control loops has been designed, the result can be exported directly to other software, like, for example, PSIM. And finally, Smart Control allows you to design the control loops in continuous domain or for analog controls, or also in discrete domain for digital controls. So when we open the software, this is the initial window that appears. And here we have different ways to define the converter plan. The first one we call a predefined topology. Here we can find different topology for DC-DC converters, such as the buck converter, boost converter, buck boost, full bridge phase shifted full bridge converter, and also for the dual active bridge. We have a predefined topology for the PFC one phase or single phase PFC boost converter, and also in the Smart Control 22024 we have the three-phase PFC boost converter. Also, in the predefined topology, we have different control structure. For example, for DC-DC converters, we can we have a single loop in order to control the output voltage or the current, for example, the current. Also, we have a control structure for the peak current mode control and for the double loop or average current mode control. So if we select this option, the average current mode control, this is the windows that appears and show you what is the design flow of the smart control. So the first step, we have to select the topology. In this case, we select the boost converter. Then we have to define the sensor stage for the current loop. In this case, we have a Hall effect sensor in order to sense the current through the inductor. And then we have to select what type of compensator we want to tune. In this case, we have three types of compensator: the type 2, type 3, and PI. And also, we have another option that is called equation editor, that you can write the transfer function of your own compensator. So after we define the inner loop, all the parameters of the inner loop, we have to select, this is the solution map that represent the relationship between the crossover frequency and the phase margin. So in the white area or the white region is all the combination that ensure that your converter will be stable. So after we select one point of the white region for one crossover frequency and one phase margin, we have to define the other loop. So in this case, first we have to select one of the sensor stage of the output voltage. We have also a voltage divider, an isolated voltage sensor, etc. Then we have to select the compensator that we want to tune for the outer loop. In this case, we have the same, the type 2, type 3, and PI. And also we can write your own transfer function of the compensator using the equation editor option. So after that, we have a second solution map in order to select the combination of the crossover frequency and phase major for the outer loops. The second way to define the plan is using the equation editor, this option. Smart Control allows to design the control loop for any power converters. Perhaps to use this option is necessary to have some experience in power converter modeling, because here you can write the transfer function in analytical way of the converter plant. So this equation editor accepts discrete seed domain for digital control and also Laplace domain for analog control. The third option is, for example, if you have a PSIM template or also you have an experimental prototype, you can measure the frequency response with a frequency response analyzer in order to get the converter plant. So in that way, you can save the transfer function in a TXT file, and then you can import directly to the smart contract. For example, in the case of PSIM, PSIM has the AC sweep function. In that way, you can get the frequency response of the converter plant, and you can save the TXT file, and finally you can import to the smart control. In smart control, when any parameters of the parameters are modified, all the results are updated automatically. In this case, we have another function, another tool that is called parameter sweep. Here you can define a range of value that you can change with the slider, the value of the input data. For example, you can change the value of the input voltage, the inductance, the capacitance, output voltage, etc. So in that way, you can see this is a sensitivity analysis in order to see how the variation of this parameter affect the dynamic of your system. So as I mentioned before, we have the solution maps, and here you can see when by moving the cursor over the white region of the solution map, the body diagrams and the transient response are updated in an interactive way. So as you can see here. Also, we have the output data report, and here you can see, for example, if you already have a PSIM template, you only want to know what is the frequency of the zero and the pole, for example, for the type 3 compensator. And here you can copy this information to your PSIM simulation, for example. Also, smart control in the analog controls recommends some value of the resistor and capacitor of the compensator. In smart control, also we can export the body plots and the transfer response of the converter in order, maybe if you want this information to use for a post-processed implementation. And after that, you have in the predefined topology, you can export directly to PSIM. That means that Smart Control create a PSIM template for you in order to verify if your control is stable or not. In the installation folder, you have a lot of documentation. This is some tutorials in order that show you how to design step by step the control loops in order to use the different types of define the converter plan. So that means that here you can find some tutorials in order that is based on the predefined topology in equation editor, or in using the TXT file from PSIM simulation. Inside each tutorial, you can find the PDF file, and also you can see the PSIM template, and this is the .tro is for the design of the smart control. So here is the design in smart control. Also, in the installation folder, you can find the smart control user guides, and this is the what's new, that it's that show you what is the new features of the latest version of the smart control. Here you have a recompilation, some links that go to the PSIM to the YouTube channel we have the example here. For example, we have the tutorials for the phase shifted full bridge DC-DC converter, and also we have a collaboration with Altair. We have some example, for example, in order to design the field-oriented control of the permanent magnet synchronous machine, for example, with PSIM and SmartCtrl. So this is a summary, and you can go to check different tutorials. Okay, today I'm going to show you how to design the resonant converter control loop using SmartCtrl. So in this example, we have a PSIM template with the series resonant converter. The first step, we want to get the converter plan. So we will use the AC sweep function from PSIM in order to obtain the frequency response. Then we save this information in a TXT file, and in SmartCtrl, we import this transfer function. After that, we tune the PI compensator. We export the design to PSIM, and we will check if the converter responds in order to see if the controller is stable or not. So we use this option because the transfer function the procedure to get the transfer function of the resonant converter is a very complicated process. So I think one of the best option is to measure the plan directly with a frequency response analyzer, or in this case, using the AC sweep. So this is the topology. In this case, we have a full bridge in the primary of the transformer. Then we have the resonant tag. We have a series resonant converter that is formed by the capacitor and one inductance. We have a transformer, and then we have a rectifier in order to get a DC voltage. So this is the operation point. The input voltage is 600 volts, and the output voltage will be 400 volts. And the resonant frequency, this is the expression to calculate the resonant frequency of the tank. So in this case, it's around 50 kilohertz. So the modulator, this is a brief explication of the modulator that I implement in PSIM. So in this case, I sense the tank current, as you can see here. And this comparator, get this is the raising age of the one of the MOSFETs. So in this case, this comparator detects the zero cruising from 0, and then we have a turn on time here. This is the turn on time with the B stable. We can with this detect the rising age. We have the Q output is high, and the duration is the T on that I predefined. So here the main idea is that this modulator phase shift the two legs. So that means that this leg is the reference, and the second leg is phase shifted from this one is defined by the T on, the on time. So this is how this modulator works. And here you can see that the voltage that the full bridge give is like AC. It's like AC voltage. So after that, I open the PSIM template, and here let me run this simulation because it takes some minutes. And now I want to show you that we are injected the AC perturbation in the on time. So here, this is important to put a name here. In this case, I called BAC. And then in the AC sweep configuration, you have to send the same source name. So in this case, the BAC. And here you can define the start frequency and the end frequency. In this case, I chose 50 hertz from 50 hertz to 10 kilohertz. This is the number of point of that PSIM will give you. And then here we define the peak amplitude of the A sweep perturbation. This is the amplitude. In this case, I select 1 microsecond in this example. Then we have to put the AC sweep proof. In this case, I want to get the transfer function from the on-time perturbation to output voltage. So this is the transfer function I want to get. And also this transfer function already contemplate the gain of the modulator. So then when I open SmartCtrl, I have to define the gain modulator equal to 1 because the AC sweep already contemplate this gain. So we have to wait some seconds. Okay. So now this is the frequency response that we get from the PSIM. So I have to save in a txt file. So I go to File, Save As, and then I call, for example, GBB. Okay, Save As. Then I have to open SmartCtrl. Okay, this is the initial dialog. So here we have to select this option, the import frequency response data from a txt file. So click on OK. And then you have two options in order to design the voltage mode control or the current mode control. In that case, we want to control the output voltage, so we have to select the voltage mode control. Click on OK. After that, we have to select the file. So here, this is the file that I saved from PSIM. Click on Open. And here we have to define the output voltage. So in this case, this is the 400 volts. And here, for example, the switching frequency, I define 10 kilohertz. In this case, only the switching frequency parameters is only used in order to calculate the modulator gain. So then I click on OK. This is the next window. Now it's time to define the sensor stage. So in this case, I select a voltage divider. Now we can calculate some gain. So I select that the voltage reference is equal to 2.5 volts. And we have to put in the PSIM simulation this gain, the 6.25 milli. So in this case, I click on OK. And then I select the PI compensator. And here it's time to define the gain of the modulator. So in SmartCtrl, the gain of the modulator is calculated by this expression. So this expression is the modulator gain. And as I mentioned before, we have to consider a gain equal to 1 because the AC sweep from PSIM already takes into account that gain of the modulator. So in this case, if I put the peak value equal to 1, the valley value to 0, and the rise time equal to the switching period, I get the gain, the modulation gain equal to 1. So this is that I put here 1, 0, and 100 microseconds. Click on OK. And now it's time to select one point of the solution maps. So in this case, I select, for example, the crossover frequency equal to 4 kilohertz. and phase barrier equal to 50 degrees. So click on update, and this is the point of I selected this combination. So after that, I click on OK. Click on OK, and this is the result that SmartCtrl show you. Let me move this here. And here you have the parameters of the PI compensator, the key P and the TI parameters, the proportional and the integral parameters. So now it's time to go to the PSIM. I have to delete the on time, and it's time to put the regulator compensator. So in this case, I have to put the parameters that SmartCtrl show. If you, in this example, we have a 1.111 micro, and the second parameter is 51.797 micro. So this is the tune. We have to calculate the error. So in this case, we have to sense the output voltage. So I select here. I have to put a label, the output voltage. And now we have to define the gain that I put in the SmartCtrl. So it's 6.25 millis. This is the gain. Also, we have to put the reference. The reference in this case is equal to 2.5 volts. And we have to put here the sensed output voltage. So let me delete this and the AC switch proof. So now it's time to check if our control loop is stable. So if I select the output voltage, here you can see that the output voltage achieved the reference. And also this is the current through the resonant tank. In this case, is like a sinusoidal, because the switching frequency is very close to the resonant frequency. So that is all. And if you have any question, please let me know in the chat, and that's it.